So let me get to the overview. First, I will describe this Sussex-Huawei Locomotion dataset, which is a pretty cool dataset. Then I will outline the general approach that we've used for this activity recognition. And I'll also describe the parts of our pipeline that are general purpose and can be used for any activity recognition. Then I'll go to the exciting part, things that we did specifically for challenges 2019 and 20. And then I'll wrap it up, show the results, and conclude with some thoughts on what works and what doesn't. Okay, so the data set. This was collected really seriously. 3 people were employed for 7 months to drive around in England and walk and run and whatnot. So there is 2,800 hours of data that's labeled with being still, walking, running, biking, driving a car or being driven in a car, bus, train, and subway. This data is recorded with 4 phones and a camera. So you can see the setup in the picture. It's taken from one of the publications related to this data set. And these phones recorded accelerometer, gyroscope, and magnetometer data. Then barometer, ambient light, temperature, GPS, Wi-Fi, and sound, plus a number of derived features. However, not all of them were used for these challenges. So these 4 were the only ones, plus some features derived from this. For challenges in 2018, 19, and 20. There was another challenge in 2021 that was a little bit different. I don't remember exactly which sensors were used there, but that one had completely different sensors. Now, I'm speaking also about the challenge in 2018. That was the first one. I won't be talking about that one today because that one was relatively straightforward activity recognition. And it's not that exciting. I mean, we were plenty excited because we won, but still, it's standard activity recognition. Okay, so this is how the data looks like. So we have acceleration data, and gyroscope is kind of similar. Let me just, okay. So when you're still, nothing happens, obviously. Then you have some periodic movement when you walk, run, or bike. And when you are in various vehicles, there's vibration that's fairly similar. Subway looks to be a bit different, but that's just one example. So that's not always like that. Now, when we look at the magnetic field, things are a little bit more interesting. So here again, we have this periodic movement that's also reflected in the magnetic field. I mean, not that the field changes, but the phone is turning, and so each axis of the field shows this periodic changes because of the movement. What's more interesting is this part. So here we can see that there is nothing special in the car or bus, but there are some disturbances in the magnetic field on train and subway, because trains and subways are electric and they generate magnetic fields. So this is actually what makes it a bit special compared to more typical activity recognition. Now, let's see what interesting things were done in these two challenges that I'll be talking about today. In 2019, we have 3 sets: a training set, validation set, and test set. For training and validation sets, we have the phone in the back, torso, and hips location. In the test set, we have it in the hand location. And this hand location is also present in the validation set, but not in the train set. And this is significant because, as you can see, validation set is much smaller. So the challenge here is to use this train data from other locations to help with classifying the test data. All data is from one user, and obviously train and validation is labeled and test is not labeled. In addition, this test data is shuffled, so it's not, things are not, instances or 1-minute segments are not consecutive in time. And why this is important, I'll explain a little bit later. In 2020, we have again these 3 sets: train, validation, and test. But here the twists are different. Again, validation set is small, much smaller than training set. Here, there are 2 complications. One is that while we have all locations for these 2, we have only one for the test set, and we don't know which one it is. The other thing is that we have user 1 in the training set, but users 2 and 3 in the validation and test sets. So again, we have to figure out if we can use this user 1 data to help us classify the test data. And again, this test data is shuffled, but even more so than in 2019. There, it was just chopped up into 1-minute segments and shuffled. Here, it's 5-second segments and they're not continuous. So there are segments missing. I don't know how exactly they are missing, but they are missing. Okay, so the general approach. First, we construct some virtual sensor streams. Then we apply some filters, and then we segment the sensor data into windows and extract features. That's very normal. Pretty much what you always do when you do when you do activity recognition. So yeah, basic activity recognition. Then we did some feature selection, which we used to do some transfer learning from this train to test set. And we also built multiple models. So these are the things that are specific to the challenges 2019 and 20. And finally, we did some temporal smoothing and we applied some semi-supervised learning. These things are also general. They don't have anything to do with those twists that were introduced in the 2 challenges, but they are, I would say, more advanced activity recognition topics. Now, virtual sensor streams. These sensor data have 3 axes, and so the first virtual stream we constructed is the magnitude, and this is very straightforward. Then the orientation of the phone is given as quaternions, which have some nice properties, mathematical, but they are also a little bit unsuitable for machine learning because they tell you about the orientation of the phone when taken all together. And in machine learning, it's often nice if each feature is informative on its own, because machine learning doesn't take these interactions between features into account very well. So we converted this into Euler angles, and the final set of virtual sensor streams is these 3D sensors that are normally in the phone's coordinate system, converted to a world coordinate system. Okay, the next step is filtering. So if we take a look at acceleration data, we can split the spectrum, the frequency, into 3 parts. These low frequency changes tell us about the gravity and orientation of the phone. And so we applied a low pass filter to extract orientation related features. The middle part is about dynamic human motion. And here we applied a band pass filter for motion related features. And finally, this upper part is noise and vibration. So here we just used unfiltered data and extracted features for vehicles. For feature extraction, we used a window of 1 minute in 2019 and 5 seconds in 2020. So we discovered that longer windows are generally preferable. And since we don't have any very short activities here, as you don't typically jump on a bus for 5 seconds, 1 minute is just fine, but in 2020 we couldn't do that because of the shuffling of the test data. Then we extracted many general commonly used features in the time domain. Then we added some physics-based features like velocity and kinetic energy, and some features that are kind of expert features for activity recognition, like the number of peaks in the signal, which can correspond to steps or something like that. In the frequency domain, we just used the spectrum, and then we binned it into, I think, 10 bins and used that as a distribution. And we added some additional features like entropy, energy, highest peaks in the spectrum, and so on. In total, we had more than 1,500 features. So we also investigated feature selection. The feature selection approach we used first ranks the features by mutual information with the class and puts them in descending order. So we get the features that are probably more relevant on top. Then, since we have such a large number of features and many are correlated, we find groups of features with correlation over 0.8, and we discard all features but the topmost one. And finally, we use a wrapper approach. So for each feature, starting with the most relevant one according to the mutual information, We include it in the random forest model, then test this on an internal validation set, and if the accuracy is well, better or not much worse, there's some margin of safety here, we keep it, otherwise we remove it. Now, the final step is temporal smoothing. And for this, we had to unshuffle the test data, which we could do in 2019, but not in 2020. The way this worked is that we selected a random segment. Then we found the segment where with its first sensor reading closest to the last sensor reading of this previous segment X. And if this minimal distance was smaller than some threshold, then we merged the segments. So our X, we appended the Y to the X, and then we returned to step 2. So our new X was no longer. We looked for the segment that is closest to this longer segment, and so on. And this worked very well, about 99% correct, which was good enough for the smoothing. And the smoothing works like this. So let's say that we have a sequence of the recognitions of train, and then there's one subway in between. And we can be pretty sure that this subway is not really subway, because you don't jump on a subway for 1 minute or 5 seconds. But we have to model this mathematically somehow. And so we use the hidden Markov model. In the hidden Markov model, we have hidden states which correspond to the true activity, and we have emissions which correspond to recognized activities. And when the true activity is train, then we recognize train, say, in 80% of the cases, and subway in 20% of the cases. And when the true activity is subway, it's the other way around. Now, we can also compute the probability of going from train to subway, and let's say this is 0.1%. So we can immediately see that if we are in here, in this train state, and we recognize a subway, this is a relatively probable thing, but actually transitioning to subway is very improbable. And since other subways don't follow, we can be pretty sure that what we see up there is in fact a mistake, and we can correct it. And the final thing is semi-supervised learning. Here, the idea is to use unlabeled data to improve the model. And how we do that? We did it in a fairly basic way. We classify test instances, and we add those that are classified with a high confidence to the training set, and then we retrain the model. Now, this model can then be used to classify the test instances again, and with some luck, the new model is better than the old one. Now, this can be repeated until we converge, or we can upgrade it in other ways, but we didn't see huge benefits of making this more complex. Maybe if we used some altogether different approach, more sophisticated, there would be benefit, but our impression was that with complications, you get diminishing returns. Okay, so now that I explained the general part, let me go to the things that were specific to the 19 and 20 challenges, so to those twists from the title of my talk. First is figuring out what the unknown location of the phone is. So here, our assumption was that when user is walking and running, phones at different locations move differently, while this is not necessarily the case when you're riding a vehicle. So first, we built a random forest model to recognize walking and running versus everything else. And this worked pretty well. Even though we didn't know the phone location. And then the next step was to train another model on this walking and running data to recognize the location. This didn't work quite so well, but still the F scores were above 80%, which is very decent, I would say. And these gave us 83% of test instances classified as the hips location, which is high enough that we were pretty confident test data does belong to the hips location. And so we went on with this assumption. The next thing was dealing with this small validation set that's different from the training set and from the test set. So if you remember, we have this wrapper approach for feature selection, and in this approach, for each feature, we include it in a random forest model, test it on internal validation set, and if the accuracy is good, we retain the feature, otherwise we remove it. Now, what is this internal validation set? This internal validation set is a part of the complete validation set, so not training set, but validation set. And in 2019, this means that it has the same phone location as the test set, but not training set. And in 2020, it means that it has the same users as the test set, but not the training set. So if we select features based on the validation set, we are essentially selecting features that transfer well from training to validation set. And this should help us to use these features on the test set. Now, let's see how well this works. And we'll also see a few other things here. So here we have one approach where we train on train set and we use the validation set for validation, as I just described. And if we don't use feature selection, we get pretty horrible results. And if we do use feature selection, the results improve substantially, which kind of shows that our hypothesis was correct. We can do transfer learning this way. However, we then tried something else. We trained on the training set plus 3/4 of the validation set, which belongs to the hand location, same as test. And we tested on the final quarter of the validation set. And we see that this works even better. So even though our idea about transfer learning was good, it turned out that this validation set is large enough so that when we combine it with a training set, the results are pretty good. And when we used feature selection here, it actually didn't work. It's hard to say why, but yeah, it didn't. So in the end, we didn't use it. Now, the final experiment was just on the validation set, because if we use just the validation set, it's very similar to the test set. And here the results are also decent. but they are worse than this combination. And so we used this best approach. Also, it turned out that if we use the hips location, this works best. So somehow the hips location is most similar to the hand location. Okay, so we did the same kind of experiment in 2020, except that here the difference between train and validation was not in the location of the phone, but rather in the persons. So we had user 1 here, users 2 and 3 in the validation data and in the test data. And the results are the same. So we can see that when we apply feature selection, when we train on train and validate on validation, the results improve. When we combine the two data sets, they improve even more. And if we use just validation, it's a bit worse. The difference is that here feature selection helped a little bit, but not significantly. Okay, so next thing is special models for vehicles. So what's this about? When the person is walking and running and maybe biking, hand moves independently of the rest of the body. And so the features and the models should adapt to this phone location, which is hand in 2019. And in 2020, they should adapt to the user, because human movement is also user specific, or at least so we believe. Now, when the person is riding a vehicle, there is no movement with respect to the user's body, at least most of the time. So the location of the phone doesn't matter so much, and the user doesn't matter so much, because it's mostly about vehicle vibrations. And this led us to believe that it may be useful to have special models for vehicles and for non-vehicles. And so we did it like this. We built one general model. Then we checked if the model outputs run, walk, or bike. If it doesn't, we use a vehicle model. If it does, we use a non-vehicle model. And of course, this general model is trained on all the data, and this one is only on vehicle data, this one only on non-vehicle data. Now, how did this work? So we can see here that in both years, using a general model plus a vehicle model is better than just using a general model. The difference is not huge, but it's there. Using a special non-vehicle model is not so helpful. And using 3 models is also basically the same as using a general and vehicle model. And so we went with this approach because it's simpler. Now, next twist is clustering users. So we see that there is a big difference between the train data and validation data. And so since these two data sets differ in the users, we thought that it might be beneficial to distinguish user 2 from user 3 as well. Now, can we do this? So our idea was that to select features that distinguish train from validation set, because presumably these features distinguish user 1 from users 2 and 3, so they are user-specific features. And then to use these features for clustering the validation set into 2 clusters, which are hopeful users 2 and 3. Then we built a random forest model to distinguish one cluster from the other, and then we classified test data with this model. And well, this also allowed us to train person-dependent models. How did this work? So here we see, here we have instances just one after the other, and these graphs show us which instances are in cluster belonging to user 2 and which to user 3. I mean, the numbering of 2 and 3 is arbitrary. We don't know who is who. But anyway, 2 clusters. And we see that data is kind of continuous, which makes sense. And it's also pretty similar for most locations. Only torso is different. Hand, hips, and well, sorry. So there's a mistake here. This should be back. So back, hips, and hand are very similar, which looked promising. We thought that we have something here. And then we went and tried it out. And because we can't subdivide the validation set too many times, we tried either having a vehicle model or having a user-specific models. And on validation data, user-specific models proved a little bit better than these vehicle models. The improvement they brought was a little bit larger. But after some reflection and complications that I'm not going to discuss here, we, on a hunch, selected this one. And it turned out that on test data, this was actually better. And we also found out later that the whole test, except for the running activity, is from one user. So apparently, we were not recognizing users with our clustering. We still were recognizing something. And apparently, our 2 clusters were somehow homogeneous, and this did help with classification a little bit, but the benefit was really, really very small. And then the final twist is here, where we have semi-supervised learning and smoothing in 2019. So when you do semi-supervised learning, the normal indicator of classification correctness is the confidence that is output by the classifier. But with the smoothing, we have another indicator of correctness, and that is how much, that is whether the base classifier and the smoothed classification agree. Because if they agree, chances are classification is correct. If they disagree, one is clearly not correct. And the expectation is that the smoothed one is better, because smoothing helps quite a bit. Now, how to take this into account is a question, and we compared different selection strategies, which I'm going to show in the next slide. So this is the baseline, no semi-supervised learning. Then this is the basic approach to semi-supervised learning. So if the confidence is high, we think it's the output is correct, and we include it in the training data, and we retrain the model. And we can take the label from the base or from the smoothed classification. one can argue for either, so they both kind of make sense. That's why they're green. Now, the next option is that the confidence of the model is high and Bayes and Smoothed classification agree. So this is something we are then very sure about. Also, this makes sense. Then we have high confidence, but Bayes and Smoothed disagree. So considering that we believe smoothed classifications more, it makes sense to use this and to use the smoothed classification as our label, because if the Bayes model is confident but it's probably wrong, such cases could be useful for retraining. It doesn't make so much sense to take the Bayes classifier's output because it's less likely to be correct. Now, next one is low confidence, and they disagree. So what this means is that the Bayes classifier is not really sure. It was corrected by smoothing, so the smoothed classification is probably correct. The Bayes is probably not correct. So it doesn't make sense to take the Bayes one. It makes sense to take the smoothed one. And then we have one combination. So this first option is that we are very sure this is correct. And the other option is this one that I just described. Again, we can take Bayes or smoothed. And the weird thing is that the best result was provided by this option that doesn't make sense. This one was 2 percentage points better than the baseline. And we used it in the end, but it's strange. So we kind of like this approach of combining the two indicators of correctness, but what we got as the best option out of this, well, we are not so sure about it. Okay, now let's put all this together and see how it all works. So this is the 2019 pipeline. We have test data, it goes to a general model, it's smoothed. We apply semi-supervised learning, so we take the output, we retrain the general model with it. And this general model and the smoothing model are trained on training and validation data combined. Then we check if the output is running, walking, or biking. If it is, we're finished. If it isn't, we go to a vehicle model, smooth again, apply semi-supervised learning again, and output the activity. And of course, these two models are trained on vehicle data. Now, how did this work? Pretty well, it turns out. So just using the general model gives us 70% on validation data. When we add smoothing, it jumps to 83%. So we see that there is a big benefit of smoothing. When we add semi-supervised learning, we get another percentage point, and when we add vehicle model, another percentage point. Now, on test data, this is a little bit different. So general model matches well, smoothing also big benefit, although not quite as large as on validation data. When we apply semi-supervised learning, it doesn't help anymore. It's hard to say why really, but these differences are small, so it could be just chance. And when we add vehicle, we do get the best result, but yeah, these three are very similar. Now, when we submitted this to the SHL challenge, our results were a bit worse because well, the whole method was not quite as refined as it is now. But still, it was enough to win. Second place competitor was not so much behind us, so 2 percentage points on test data, but for some reason they significantly underestimated their accuracy. So when the competition results were announced, they were surely very pleasantly surprised, unlike other competitors who overfit and were unpleasantly surprised. Then let's take a look at 2020. Here, things are a little bit simpler. Again, we have the general model, semi-supervised learning. We only need to train this model. There is no smoothing model. Then we check the activity. Go to the vehicle model if it's a vehicle activity. Do semi-supervised learning. Output. And this one is again trained on vehicle data. Now, how did this work? If we take the general model only, we get 79%. Then we have 1 percentage point jump with semi-supervised learning. And we can see that this is retained on test data. So semi-supervised learning does help sometimes. If we add vehicle model, we have quite a big improvement, but not so big on test data. And our submission was again a bit worse. We made some mistake, and we placed third in this competition. The winner was quite a bit better. Again, it happened that they underestimated on validation data. Second place competitor, well, would be third place if we didn't screw up when we submitted, but we did, and so they weren't in the third place. We were. Anyway, they were very close to us. Okay, so what can we conclude from all this? First, we see that temporal smoothing is very powerful, and also it's not super difficult to implement. So I think it's quite worthwhile to do. I mean, it won't work on all data. If you have a lot of very short activities, or if the changes between activities are essentially random, then it won't work. So it, and also an important consideration here is that you need realistic data. So if you record your data in the lab, the transitions between activities will not be realistic, and it's not going to work too well. And also, if you get data that's shuffled, it won't work so well. But that's an artifact of the competition, because yeah, apparently the organizers were trying to prevent this temporal smoothing for some reason. Okay, then feature selection for transfer learning. We learned that it works well, but combining train and validation data works even better. That's true even if the validation data is small. Now, I don't know what would happen if it were even smaller. So we didn't try that out. We could, I suppose, we could just discard some validation data, see what happens. It would be an interesting experiment, I guess. Semi-supervised learning and multiple models help a little. Nothing very dramatic, but in some cases it improved our results. Now, another conclusion is that most interesting ideas don't always work best. So that person clustering, we were quite proud of it, but it didn't work so well. And our idea of combining smoothing with semi-supervised learning was also kind of cool, but it worked very strangely. And well, a final conclusion is that you cannot always win. So we won in 2018 and 19, but in 2020 it didn't pan out. But still, I hope that the things we did and what we learned was interesting, and that you enjoyed this talk. With that, I conclude. Here are pictures of all the colleagues who were involved in this research, because obviously I didn't do everything. So thank you for your attention, and I'll be happy to take any questions you might have.
Thank you, Mitja. I was just waiting to see if Mitja would want to have this final Q&A, but I'll take it from here. And so I think my job now is to understand if there are questions, and I see that Horan already has one. So go ahead, Horan.
Yeah, thanks a lot, Mitja, for the great presentation. One question that I have, maybe I have two, but I will start with one. So did you also try, I guess you were using, I want to just call it classical machine learning.
Yeah.
You know what I'm aiming to, right? So did you also try something else like deep learning?
Actually, in 2018, which I was not talking about today, we did. There, our final best result was an ensemble of classical and deep models. And they were kind of comparable. And of course, ensemble was better than either individually. In these 2 years, we didn't try deep learning because, well, first, because we learned in 2018 that it doesn't bring such a huge benefit. Second, because as soon as you start with deep learning, everything gets more complicated. The models are slow to train, difficult to tune. And well, there was some time pressure, and we wanted to try all these other things that I talked about today. And if we wanted to do that with deep learning, we would never have finished on time.
Okay, I see. So like, but in real, maybe you would suggest to do it because it was a competition, but if you would have your own real data, maybe you would consider to do it, or?
Yeah, I don't know. I mean, when we look at these SHL challenges, we see that deep learning is doing well, and it won the 2020 challenge. So I would say it's worthwhile to explore it. I am not very fond of it myself, to be honest. I mean, in the context of activity recognition, at least. But yeah, I mean, it can work well, and it's also a bit fresher than your classical machine learning, which has been done to death on activity recognition. So yeah, if for people who are considering doing something new in the field of activity recognition, do give it a try, sure.
I see. Thanks. So Thiago, yeah, I would have another question, but maybe we let the others first if someone wants to ask some.
I think you can ask it, and I'll ask others to also raise their hand if they have more questions.
Okay.
And in the meanwhile, go ahead.
Yeah, sorry, Mitja, for having a second question, but
No, it's fine. Questions are welcome.
What I was also thinking of, you showed this one slide, you don't have to go back, where you said, okay, we have a validation set of like, I think 1/4 was like, you splitted it somehow. And I was thinking, do you think it would make sense to do like k-fold cross-validation to like, you know, somehow shuffle? So
yeah. So we did that. I didn't explain it, but yeah, we split it in 4 folds, and we repeated this 4 times. So when I say 1/4 for testing, 3/4 for training, we repeated this 4 times.
Yeah, perfect. That was exactly the question.
Yeah. And yes, I think that's the way to go when you have a smallish set, because how you split it can affect your results a lot.
Exactly. Yeah. Okay. Yeah. Okay. I was just wondering. A small last question, maybe just very small. Can you like explain a bit more the smoothness? What do you mean by that? Like, what do you mean exactly by smoothing?
So it's this thing with hidden Markov models that I talk about. So let me reshare the screen. I think it will be easiest. So okay, so it's this. The idea here is that activities don't change very frequently, so you don't get short activities like this one, and so you can smooth out mistakes like this.
Yeah. Okay. I see. Okay. I mean, in the end, you could even like put a model on this, but okay, you did it with hidden Markov. I see, but I get the point now. Okay. Yeah, Mitja, thanks a lot.
You're welcome.
That's it from my side. Thanks again for the presentation.
Okay, so I also have one question, Mitja. So you have had some expectations regarding your final slide combining smoothing and semi-supervised learning, and it didn't work out in this particular data. And so, but it had a rationale, and so I think it makes sense. Did you have the opportunity to experiment with the approach in other data sets, or even if something that you already have worked on in the past, or not yet?
Not really. So, okay, let me provide some meta explanation. We, of course, participated in the competitions. Things went pretty fine. And as researchers are wanted to do, we wanted to produce a nice publication about this. And when we started preparing that publication, we realized that there are many inconsistencies in what we did, and that it would make sense to try all sorts of things. And in the end, this took a long time. We are now on the verge of submitting the paper that basically describes what I presented today. And well, we were kind of short on energy and time to do even more. So I think this is it until we get some new problem of this kind that we need to solve. But to do it just for the sake of research, it's not in the cards, I think.
Thank you. Are there any other questions? Okay, so I think in the name of all, I would like to thank you for the very interesting presentation and thank the audience for participating in another one of our seminars. These are seminars of the project WideHealth. I think most of people are here are within the project, so but everyone is invited. And if you have an idea for a future seminar, feel free to let us know and we will try to organize it. So thank you once again, Mitja, and see you soon.
Bye.